Yes. So after pericyclic reactions, next we are going to start with new chapter, photochemistry. Okay. Keep reading photochemistry. So mostly you have some numerical relations in physical chemistry, but your maximum organic photochemistry we are going to discuss. Means with the help of any photon or with the help of any light energy, one can easily convert any organic molecule into a new organic molecule. So interconversion of functional groups, especially organic functional group, by irradiating with a light energy. So photochemistry is a study of a preparation of variable organic molecules by irradiating with a light energy. That is called photochemistry. So generally we can transfer energy or we can give energy for any molecule in two different ways. That molecule may absorb energy by supplying heat energy. That molecule may absorb energy by giving a light energy. Okay. Any reactant can take energy in two ways. One is heat energy, second is light energy or photochemical energy. So, but giving energy in the form of heat is most convenient and very easy as compared to light energy. Why? Because you can give heat energy directly, but photochemical energy is not the easiest process. So thermal reactions are very easy to compare as compared to photochemical reactions. Thermal is very efficient as compared to photochemical, but even though photochemical is not the easiest process, but they have its own importance. Okay, so all photochemical reactions are not easy to work out, but most of the thermal reactions are very easy to work out. But even though photochemically most of the organic reactions are not possible, but still that reactions are easily preferred in thermal conditions. So that's why most of the industries they will prefer only thermal reactions but not photochemical reactions. So even though photochemical reactions having some deviations, even though they have less importance, but some photochemical reactions are there which cannot be prepared by thermally. So that's why photochemical reactions having a separate branch. Even though they have less importance, but whatever chemical reactions, especially some chemical reactions which are takes under photochemically, which is impossible to prepare under thermally. Okay, you write the points, then you will go through photochemistry. So what is photo indicates? So here you write photo indicates light or photon. Light or photon. It is a form of energy. Photo nothing but form of energy. It is a form of energy. Okay. Now see what is photochemistry? The study of organic synthesis. It is a study of organic synthesis by irradiating nothing but exposing. We are showing the sample. The study of organic synthesis by irradiating light on a organic mixture. This organic mixture is also called sample. Organic mixture is known as photochemistry. Is known as organic photochemistry. If you take that sample, organic sample, that is called organic photochemistry. Organic photochemistry. The study of organic synthesis by irradiating light on a organic mixture. So here we are preparing a new organic molecule and we are exposing that organic sample with a light energy and we are preparing a new organic molecule, that is called photochemistry. Okay. Now see. Energy is transferred. Energy is transferred to reactant in two ways. Energy is transferred to reactant in two ways. Two ways we can transfer energy. So what is first form of energy? So this is called thermal energy. Thermal energy. Thermal energy. Energy is transferred to reactant in two ways. First one is thermal energy. Second one is what? photochemical energy. Photochemical energy. Two types of energies we can transfer to reactant. Thermal energy or photochemical energy. So what is thermal energy? So giving energy for reactant in the form of heat. So we are giving energy for reactant in the form of heat energy, that is called thermal energy or thermal reactions. Okay, so thermally we are activating the molecule by giving energy in the form of heat. Simply indicates we are heating the sample. Okay, in this case we are exposing the sample towards sunlight or by using any light energy, that is called photochemical energy. Okay, now see, write down. Providing energy in the form of heat. Providing energy in the form of heat is known as thermal energy or thermal reactions. Thermal energy. Providing energy in the form of heat is thermal energy. Same. Providing energy in the form of light energy is known as what? Photochemical energy. Photochemical energy. So we are giving energy in the form of heat is thermal. Giving energy in the form of light is called photochemical. Okay. See, if you compare thermal reactions are very easy as compared to which one? As compared to photochemical. As compared to photochemical reactions. What is the reason? Why? Because photochemical, it is a time taking process. Much more time you need to spend on photochemical, but here it is in our hand. If reactant is not responding, we are keep on increasing the energy very easily. So we can say thermal reactions are very easy as compared to photochemical reactions. Thermal is more easily we can work out in laboratory as compared to photochemical. Okay. So if you see, thermal reactions are industrially viable. Industries are highly preferred thermal reactions. Viable means preferred. Thermal reactions are industrially viable as compared to photochemical reactions. Thermal reactions are highly or industrially viable as compared to photochemical reactions. So which is very easy to work out between thermal and photochemical? Thermal reactions are very easy. Industrial, it is very easiest way. But photochemicals are not easy. But even though photochemical is not easy, if you ask why you are doing these photochemical reactions, means some specific organic reactions are there which can be done only with photochemical, which cannot be done with thermal. Okay, so that is importance of photochemical reactions. Okay, next here you write importance of photochemical reactions. HV nothing but photon, you remember this. Importance of photochemical reactions. So why we are using photochemical reactions even though they are not preferred? Which is preferred here? Thermal is preferred. Photochemical is not preferred, but still we are using photochemical reactions. Why? Because they have its own importance. So first one is, see, you know this point, photosynthesis. It is also called carbohydrate synthesis. We can prepare carbohydrates with the help of light energy, right? We know this reaction. When carbon dioxide reacts with water molecule that is exposed with photon, light energy, that is nothing but a sunlight. Then what happens? There is a formation of a carbohydrate or not? C6H12O6 plus there is a loss of oxygen. See, this cannot be taken by a thermal reactions. See, light is giving some energy to any plant or any tree, so that will intake carbon dioxide and water, okay, and this energy is taken by these two and finally converted to carbohydrate. So now we are supplying energy or not? We are supplying energy and plant is taking carbon dioxide as well as water and it is preparing carbohydrate. So that carbohydrate is a working metabolism process for the corresponding plant. So right now it is releasing oxygen or not. So this is called photosynthesis reaction for the generation of a carbohydrate. So plant is taking carbon dioxide and water, and while irradiating with the light energy, now these two are get converted to carbohydrate and oxygen. Okay, we are preparing energy or not. So we are preparing food for the plant. So that's why plants will grow. So this cannot be happen. Suppose if sunlight is not there, can you heat the plants? No. So if you think that this energy and light energy and thermal energy, if you think both are same, suppose if light energy is not present, will you heat the plant? No, it is impossible. If you heat the plant, it will die. So which means we are not generating carbohydrate directly thermally. So we can generate only by using light energy. Even though it is a slow process, but they have its own importance. Right. That is first one, photosynthesis. You take this in preparation of carbohydrate. Preparation of carbohydrate. Carbon dioxide combines with the water molecule gives C6H12, O6 then followed by 6 equivalents of oxygen. Okay, so it is mostly in preparation of carbohydrate. In preparation of carbohydrate. Okay, it is used in preparation of carbohydrate. Now it is also used in photochemical reactions are also used in vision. When sunlight is directly contact with our eye, it is used to convert trans-retinol to cis-retinol. Okay, so when directly light energy contact on any eye, that eye usually converts trans-retinol to cis-retinol. It is not possible under thermal. Which means if I take a retinol, this is double bond and see this is double bond and here it is a aldehyde. This is called trans-retinol. And if you focus this double bond, it is a trans orientation above and below. Right now this is on photochemical. If I irradiate, then what happens? See, trans becomes cis-retinol. Okay. Now see, this becomes here one of the double bond and see this is aldehyde and here it is methane. See, now this double bond is which one? Trans. Right now the double bond is converted to cis. So trans-retinol can be converted to cis-retinol. So generally it is done by using a photons. When photons directly contact with the trans-retinol, it is present in our eye. Okay, trans-retinol after interacting with the light energy converted to cis-retinol. So this is not possible if you expose with a heat energy. If any person directly watching a heat energy, that heat energy never converts trans-retinol to cis-retinol. It is possible only under photochemical energy only, means sunlight. That is one of the advantage. So trans-retinol converts into cis-retinol while irradiating any light directly on eye. So when you see directly sunlight, this may happens. Clear? Next, some selective reactions are there. Suppose see, if I take a 1,3 butadiene, thermally if I take, you may expect this is minor and this is major. So this is only 10% and this is 90%. Which is major? This molecule is major, large molecule. But whenever if you take photochemically, whichever is minor, that is major in this one. Okay, so this is major under photochemical, which means in photochemically whatever products are minor, in case of thermally they becomes major in photochemical reactions. Now when diene combined with one more diene under thermally, if only monomer is involving, you will get this strain molecule. But when dimer is involving, you will get this one. It looks like a Diels-Alder reaction. Suppose see if I take this two, this is diene and this is one more diene. Two dienes are participating now. So if I say thermally, if it is combined together now, so will you get this? What is this reaction? Diels-Alder reaction. Diene plus dienophile. So Diels-Alder preferred under which case? Thermally. So thermally this is major. And same reaction if I participate, see, this is a electrocyclic reaction, pure electrocyclic reaction. Then what happens? See, we are preparing a strain molecule like this. This is preferred under photochemically. This kind of reactions are preferred under photochemically, but this is preferred under thermally. So remember, strain molecules are easily prepared under photochemical but not under thermal. That is advantage of photochemical reactions. Highly strained molecule we can prepare very easily under photochemical but not under thermal. Next, so we can prepare a major advantage, preparation of strained molecule. Strained molecules can be easily prepared in this one. See, if I take this molecule which is undergo cycloaddition, see this is undergo cycloaddition, now you may get this product. This is called quadricyclane. Now we are getting a quadricyclane. This quadricyclane is prepared under photochemically easily but not under photochemically. Suppose if you work out reaction with photochemically, this won't exist. Photochemically strained molecules are not possible. You can prepare but yield is very poor. We can ignore under thermally but we can prepare under photochemically. Okay. So when this is undergo 2 pi cycloaddition, already we learned 2 pi preferred under photochemically. In pericyclic we confirm. So if any molecule, if it is giving a strained molecule, that is easily accelerated under photochemically. So we can prepare strained molecules under photochemical conditions. Quadricyclane. So that is importance of photochemical reactions. We can prepare carbohydrate and we can use for conversion of trans-retinol to cis-retinol, and we can use to prepare a strained molecule especially by using mono system, and one more is preparation of a strained molecule by using a pericyclic reaction. So these are the importance of photochemical reactions. Next, sources. What are the sources of photochemical reactions? Sources of photochemical reaction. First one is, what is this? Sunlight. Sunlight is a source for photochemical reaction. Next is mercury lamp, and one more is tungsten lamp. Mercury lamp and tungsten lamp. Okay. So mercury lamp is used for UV and this is used for visible radiations. Lambda UV radiation we can use for sunlight, we can use as a photochemical irradiation, and directly we can also use mercury lamp, and one more is tungsten lamp. So mercury lamps are used for UV radiation. Okay, and what about this one? Visible radiation, UV visible radiation. So tungsten used for visible radiation, mercury used for UV radiation. Okay, now especially these mercury lamps are very important one. They are available in T different modes. Low pressure mercury lamps, moderate pressure mercury lamps, then one more is high pressure mercury lamps. 3 types of lamps are there. Okay, so sources are only 3 sources are present: sunlight, mercury, and one more is tungsten. Mercury lamps are used for UV. Okay, so they are available in 3 different forms: low pressure, moderate pressure, one more is high pressure. Okay, now if you want to do any photochemical reactions, see, photochemical reactions, if I use this symbol, that is called photochemical. Okay, photochemical reactions are highly stereospecific or highly specific, you write, highly specific reactions. So required, what is the required for this one? Required suitable lambda. Required suitable lambda. So if you want to participate in chemical reaction, range is not required for any selective functional group. There is a requirement of a specific wavelength. So photochemical reactions are highly specific reactions. Highly specific means, suppose if you want to participate one selective part in a photochemical reactions, only that part suitable lambda is required. Which means if you take any range, they won't participate. Okay, suppose I am taking a mixture of reactants. If 10 reactants are there, one of the reactant, if you want to participate, select a suitable lambda max. Lambda nothing but a wavelength. Select a suitable lambda. If that lambda matches to one of the reactant, only that reactant will participate in the reaction. Remaining won't participate. That is called specific reaction. Suppose if 10 functional groups are there, 10 functional groups never participate in photochemical reactions at a time. They require their suitable lambda, suitable wavelength. If you irradiate with suitable wavelength, then only that particular functional group participate in chemical reaction. So that's why it is a specific reaction. Okay, but in case of thermal, it is not like that. Suppose if 10 functional groups are present, almost all functional groups will take energy. But in this one, it is not like that. So we need to irradiate with suitable lambda, then only that functional group will participate in photochemical reaction. So that is called specific reactions. Okay, so if you pass total wavelength, suppose if you are passing a wavelength in the range of 170 to 300, 350, 400 like that, that sample never take energy. Why? Because it is a specific. Suppose in that particular reaction, if you assume that 150 is sufficient, and if you pass 150, definitely that functional group will participate in chemical reaction. So that is the general photochemical reactions. So which are highly specific reactions, required suitable lambda. So if suitable lambda is present, then only that particular functional group will participate in reaction. Suppose see, this is one sample. Suppose one functional group is present. So this is M, just to assume that M is a molecule. So this molecule carry 150 nanometers of energy to participate in chemical reaction. So if you participate a light energy which carry 270 nanometers, so this won't participate in reaction, no use. Now I am participating a light energy which having 150 nanometers, then only this will participate in reaction. Okay, suppose I am using a reaction, a molecule which carry 2 functional groups. Otherwise I am taking 2 molecules. This is M1 and here it is M2. So energy for M1 is 150 nanometers, energy for M2 is, so let us say 220 nanometers. Now say I am passing a radiation, this is a radiation, and here also one more radiation passing. If I pass a radiation of 150, which molecule will participate? This will participate in chemical reaction. And if I participate M2 molecule in photochemical reaction, we need to transfer 220. If I transfer 220, this will participate. Which means out of these 2, only one will participate in chemical reaction. That's what is called specific. Specific means every molecule or every part in a molecule. Right now here 2 molecules are present. These 2 molecules may be present in one molecule at a time. Such as double bond in alcohol, double bond in triple bond, alcohol, amide, halogen, like that. Multiple functional groups may be present within the molecule. Okay, on that time, based on the wavelength which we are incidenting on the sample, only one particular functional group will take that energy and they will participate in the reaction. So that's why it is called specific. Specific means even though 1000 functional groups are present, out of the 1000 functional group, for a selective functional group, If lambda max is matching or lambda is matching, only that functional group will participate in reaction. So that is called specific reactions. So all photochemical reactions are highly specific. Until and unless if you are not maintaining this radiation, these two molecules never participate in reaction. Is it clear? This point is very, very important. Suppose if you heat this molecule, thermally they will participate. Now both molecules will take average energy. Both molecules are start participating in reaction. Thermally there is no specific energy is required, but photochemically specific energy is required. Right? See, if you are standing early morning in front of a sunlight, is it different or if you stand on afternoon time? So if you stand in afternoon time, that is also sunlight. Early morning is also sunlight. Both are same? No. Both are not same. Here also same. So two molecules are present which require a specific energy. Specific wavelength if it is present, then only that molecule will take energy. If you think that D vitamin is there in sunlight, if you stand exactly at afternoon session, 1 o'clock or 2 o'clock, D vitamin will not come. Okay? So complete dehydration will take place. Here also the same thing. Based on wavelength, property changes. Based on that property only, molecule will participate in chemical reaction. If you pass 270 nanometers, no reaction. So now it is reaction takes place. Okay, now see, specific radiations are generated by, how to generate this specific radiation? Generated by filters. You know, see what I am saying, suppose if wavelength is keep on changing, so 270, 230, 250 like that, that radiation is not required for the sample, only constant wavelength is required, right? So in order to generate this specific reaction, we require specific radiation or not? See, we want 220. If you want to get 220 nanometers of wavelength for a specific reaction, there is a specific radiation is required. Right or not? Say they require 150 nanometers of energy, wavelength is required. So we need to generate 150 or not? Until and unless that radiation is not 150, they won't respond. So for generation of a specific wavelength, we require a filters. Filters are used to convert a mixture of radiations into specific radiation. Mixture of radiations are converted to specific radiation is nothing but a filter. Okay? So specific radiations are generated by filter. So what are filters? Filters are rectangular glass vessels. Rectangular glass vessels used to generate, what they generate? Used to generate specific wavelength. Specific wavelength. Specific wavelength of which one? HV. What is HV? Photochemical radiation. Filters are rectangular glass vessels used to generate specific wavelength. Suppose see this is a filter. Now this is a filter. Rectangular filter now. See this is a sample, reaction sample. Now sample required 220 nanometers of wavelength. Okay. Now what we are passing, see we are passing a radiation. See this is a sun or light radiation. Suppose it is UV visible. UV visible we are using. So in UV visible what is the range? 200 to approximately 800 nanometers. Now this all radiations we are passing on this filter. Then what happens, see this filter is specially designed such a way that which will allow 220 only. Filters are rectangular plates, a small porous will be there, holes will be there, which will allow a specific wavelength. Okay. Now in this one only certain wavelengths are going to be irradiated now. See, only certain wavelength. What is that wavelength here? 220 nanometers. Suppose if I am changing the filter, this is constant every time. This energy is constant, 200 to 800. So whichever energy is required, for our photochemical reaction, we are placing that particular filters here. Suppose I want 270, I am replacing this particular filter into 270 filter. So now the filter is made up of 220 nanometers hole. So with this particular holes only, radiations are filtered, and finally that will pass around sample tube. So finally sample will participate in chemical reaction. So they are called rectangular vessels, also called filters. Filters used to filter wavelength of reactant in a suitable lambda. Some filters are there, just you concentrate. Filters, cut off wavelength. Pyrex filter is here. So here this is 270 nanometers, less than 270. Next followed by borax filter, 260 nanometer. Vicor filter, 220 nanometer. Then followed by quartz. So this is almost all 170 nanometer. So this is allow above 270. So below 270 they won't allow. So this is allow above 270 nanometers of wavelength. All samples are going to be placed more than 270. Now here also same. Which will allow above how much? 260 nanometers, and here also see which will allow above 220 nanometers. Radiations are going to be allowed. Lower radiations are not allowed. Means they are high energy. So which is allow 170 nanometers. More than 170 nanometers of wavelength radiations are allowed. Okay. So this never allow below 170. 169 is not going to be allowed. Now in this one it will allow only more than 220. 270 is allowed, 220 is allowed, 225, 230, everything is allowed here. But 219 is not allowed, 217 is not allowed, 180 is not allowed. So lower than this is not allowed. Less than 260 means less than 260 is not allowed from this filter. Suppose if I place a borax filter, is it 220 allowed? If I place a borax filter here, this I place, borax, suppose if it is a borax. Is it 220 comes out from this filter? No. Which is a suitable filter here? I want 220. I want 220. So suppose see quartz less than 170 is not allowed. More than 170 is allowed. More than 170 means? Okay, so this is readily allow above 270. Readily allow above 170. Readily allow more than 220. Now here 220 placed in between 170 to above or not? Yes, above 170 220 is there, so definitely 220 is allowed. So they are glass vessels, so used to make any photochemical reaction, suitable glasses are required. Next, keep heading photochemical energy. Next is photochemical energy. After knowing filters, one should know about what is the photochemical energy. So what is photochemical energy? The energy of a radiations which is responsible for chemical reaction is nothing but a photochemical energy. That photochemical energy transferred from UV visible radiation. So UV visible radiation is a photochemical energy for most of the organic molecules, and this photochemical energy used to make excitation of an electron. In the same way it is also used to break a bond. So indirectly what I am saying is photochemical energy responsible to excite the molecule, at the same way that is also responsible to break the bond. So photochemical excitation, photochemical bond dissociations will take place under photochemical energy. Okay, right. Better. The energy produced by light or photon, for organic synthesis is known as photochemical energy. For organic synthesis is known as photochemical energy. Okay, next. The suitable photochemical energy is lambda UV visible. So you write this 200 to 800 nanometers. Lambda UV visible. Okay, next. In photochemical reactions, this energy suitable for which one? This energy is suitable for electronic excitation and bond dissociation. So indirectly I am saying that for photochemical chain this energy is sufficient. Okay, so in photochemical reactions this energy is suitable or sufficient for electronic excitation. One more is photochemical dissociation. For breaking a bond or by activating a electron to exit from ground state to excited state, this energy is sufficient, I am saying. Indirectly this is UV spectroscopy. UV spectroscopy is electronic spectroscopy where electrons are transferred from one state to other state. Okay, now if I take lambda UV is C, lower wavelength radiation, high energy or low energy? Lambda UV. So here lower wavelength radiation means wavelength is very less. What is the wavelength here? Wavelength is almost all C, lambda 200 to 400 nanometers. So this is high energy radiation. So we can say wavelength is very less, so we can say high energy radiation. Now simple olefins will take this energy. Simple olefins are isolate molecules will take. Okay, so here simple molecules or olefins, simple olefins will falls in this range. So some UV spectra information is required in photochemistry. So lambda UV, lower wavelength radiation, lambda length is very less but energy is very high. So when lambda is very less means energy is very high, wavelength is less means energy is very high. Okay, so the high energy radiation, high energy photochemical energy or high energy radiation which is required to fall on a sample where they required high energy to absorb. If gap is very high, they required high energy, especially sigma to sigma star and pi to pi star belongs to this range. Okay, even pi to pi star they are changes based on conjugation, but mostly they are ranges in between sigma to sigma star. Suppose if sigma to sigma star transition is taking place, now electrons are present here, this electron want to exit from here to here. So what kind of radiation we need to transfer? Now we need to transfer UV. Why? Because UV radiations have a sufficient energy to transfer electron from sigma to sigma star. Visible is impossible to transfer this electron. So it will come one more time in UV. Right now you remember, in order to make sigma to sigma star electronic transition, UV radiations are sufficient. Okay, next. Second one, in this case, lambda visible. What about lambda visible? Lambda visible, see, higher wavelength radiation. Higher wavelength radiation, if wavelength is very higher, which means is it more energetic or less energetic? Less energetic. And radiations are ranges from 400 nanometers to 800 nanometers. 400 to 800 nanometers, that is this one. Is it low energy radiation? Now it is low energy radiation. This radiation is very low and mostly conjugate olefins. Carbonyl compounds. Okay, so what are carbonyl compounds? Aldehydes, ketones, etc. So conjugate olefins, carbonyl compounds will fall in this region. Okay, so when conjugation is present, what happens? Pi 2 pi star is possible in this range. In the same way, N2 pi star also falls in this range. Yet this pi 2 pi star, this is different. It is an isolated olefin, only simple one double bond. It is a conjugated double bond. Conjugated double bond means like this. Now here this is simple olefin. Carbon-carbon double bond, here carbon-carbon double bond is present, which is continuously repeating. So when conjugation increases, gap between pi 2 pi star decreases. Here see this gap is very high or not. Suppose if it is a pi 2 pi star, gap is some distance is there. But when double bonds are increasing, gap will be regularly decreases. Okay, so here this gap, suppose if I take pi 2 pi star, this is pi and this is pi star. Now here one pi electron is present, it will exit under like this. So this is possible both in UV as well as visible. But in UV this gap is very less, gap is very high. But in visible gap is very less. So this gap will be decreases due to increase in conjugation. As conjugation increases, as number of double bonds increases, here gap will be regularly decreases. When gap is very less, excitation takes place very fastly. So finally, you can write like this. I am using a UV visible radiation, that is 200 to 800, so that may ranges to 36 to 143 kilocalorie per mole. It is the energy of photochemical reactions. 36 kilocalorie per mole to 143 kilocalorie per mole. UV visible radiation having a energy of giving energy from 36 to 143. 36 kilocalorie per mole to 143 kilocalorie per mole. So that is photochemical energy. So first we learn importance of photochemical reactions, then sources of photochemical reaction. Then in that source of photochemical reactions only we learn what is photochemical energy. Okay. Next, this one, activation and deactivation. Activation and deactivation of molecule. So what is activation and what is deactivation? So first you should write about what is a ground state. So what is ground state? What is ground state? It is a state of a molecule where electrons are or corresponding molecule is highly stable with low energy. It is a state of a molecule where molecule is highly stable and low energy. What is excited state? It is a state of a molecule where molecule is unstable and high energy. Right or not? So in order to understand activation and deactivation, one should know about states. So generally we have ground state as well as excited states. Excited states are nothing but higher energy states. Ground state nothing but the lowest energy state where electrons are already almost all paid. Maximum they are paid only. So it is the lowest energy state of a molecule. And we can also say highly stable state of a molecule. That is called ground state. Right. Right on? Ground state. The state of a molecule having what they have? Having low energy and stable, low energy and stable property. Mostly properties are also stable, low energy and stable. What about excited state? Now here also same. The state of a molecule having high energy, right? High energy and unstable. High energy and unstable property. Low. Ground state is a stable, excited state is a unstable. That is the only key point. Ground state having a low energy and molecule is stable. Excited state having a high energy and molecule is found to be unstable. So we can say unstable property. Suppose if I take sodium, sodium is photochemically excited by using 589 nanometers. Then what happens? Sodium is undergo excitation like this. Right? So what is the electronic configuration of sodium? Now generally see this is 3s1 and here 3p0. Right? Then what happens? It becomes a 3s0, 3p1. So this is one example of excitation. 1s2, 2s2, 2p6, 3s1. Now 3s1 undergo excitation, that will give 3s0. Means that electron excited to 3p. So which means it is photochemically excited. So this is a ground state or no? Sodium ground state and sodium excited state. Now if I take a diene photochemically excited by using 220 nanometers. Now this is excited state of a molecule. It will be written like this, excited. Excited molecules are written like this. Now what is electronic configuration? Psi1 square, Psi2 square, Psi3 0, Psi4 0. See, photochemically you can activate a atom, photochemically you can also activate a molecule even. Don't think that photochemically we can activate only atoms. Photochemical energy also sufficient to activate even for a organic molecule, not only for atom. Sodium, potassium also they will take electron from one state to other state. Okay. Now this particular energy sufficient to excite this electron from 3s level to 3p. Now here also see it is a molecular energy levels. Then can you write the electronic configuration? Psi1 square, Psi2 1 and what is this? This is Psi3 1 and this is Psi4 0. Now how much energy is required for excitation here? 220 nanometers. When 220 nanometers energy if you expose to this particular molecule, now this is excited, which means electron is transferred from HOMO to LUMO. That is called photochemical excitation. This is called activation. If electron is transferred from HOMO to LUMO, if electron transferred from ground state to excited state, that is called activation. So once if you activate it, then definitely it should be deactivated, right or not? Not only jumping. If you jump and if you leave it, nothing will happen. Okay? Once if it is jumped from lower energy level to higher energy level, definitely it will come back to original state only, right or not? So during coming from activated state to ground state, that is called deactivation. You write clearly? Deactivation. Okay, right. So what is our target? Our target is to make deactivation. So electronically, if any molecule is excited, they may undergo deactivation in following possible ways. Many possible I will show. In how many possible ways this excited molecules get deactivated. Our concept is activation. This is activation. Two possibilities of activation I shown with one atom as well as one molecule. Now I am showing how to make a deactivation. Okay, right. See, electronically excited molecule or atom get deactivated by following ways or following methods. Following ways it may be get deactivated. So electronically excited molecule may be get deactivated by following ways. Many ways you can deactivate a excited molecule. First way, deactivation, simple deactivation. So first is simple deactivation. Okay. See, this process is called deactivation of a molecule by releasing in the form of so molecules get deactivated by releasing energy. Okay, by releasing energy. So it becomes a ground state without participating in chemical reaction. See, is it releasing energy or not? Now, without participating in chemical reaction. Without participating in reaction, they will come back to ground state. That is called deactivation. Which means, see, this is ground state molecule. It is get activated. That becomes a M star, right? It will be come back to ground state only, which is going to release some energy, but they never participate in chemical reaction. Okay? So now this energy becomes a heat energy. Right or not? See, whenever if it is coming back, what happens is some energy is going to be released here. That energy I am saying heat energy. This is a deactivation by releasing energy in the form of heat. Electronically excited molecule is getting deactivated. Deactivation is nothing but what? It is taking energy and jumping into high energy level. So whenever if it is jumped into higher energy level, they need to participate in reaction. Otherwise they want to come back to its original ground state. Suppose if they not participate in chemical reaction, two possibilities will be there. They will come back to ground state by releasing energy. Otherwise they will come back to ground state by releasing energy in the form of light. Okay? First possibility, deactivation by releasing energy. That energy in the form of heat energy. Next possibility, deactivation by releasing energy in the form of light. Okay? Now two types of deactivations. Say why molecule is excited? We are giving energy. That's why molecule is excited. When molecule is excited, they want to participate in chemical reaction. Otherwise they want to come back to original state by releasing their energy. So whenever if it is coming back to ground state, they will release energy in two ways. First way in the form of heat, second way in the form of light. Now this is first deactivation. Deactivation by releasing energy in the form of heat. That is this one. Now second one. It is also a deactivation process. Now it is second way of deactivation. How to deactivate? See, deactivation of a molecule. Deactivation of a molecule by releasing energy in the form of energy in the form of light. By releasing energy in the form of light, that is mostly without participating in chemical reaction. That is constant. So, without chemical reaction, without participating in reaction, without participating in chemical reaction, that will be a photochemical deactivation. So here ground state molecule is get activated and it becomes a active molecule. Now it becomes deactivated and this will be released in the form of light energy. Okay, this light energy is nothing but a luminescence. Okay, this light energy is nothing but a luminescence. There you will say the word luminescence. Luminescence are generally two types: fluorescence and one more is phosphorescence. Okay, luminescence generally releasing energy in the form of light is called luminescence. Luminescence is generally two types, fluorescence, one more is phosphorescence. So here generally converts from singlet to singlet, S1 state to S0 is called fluorescence. Okay, then one more is triplet states to S0 is called phosphorescence. It will come one more time in Jablonski diagram, there I will explain clearly. Right now you focus on only 2 points. Activated molecule get deactivated by releasing energy in the form of heat. Activated molecule get deactivated by releasing energy in the form of light. So in these two cases, activated molecule never participates in chemical reaction to give product. Product formation is not exist. Only get deactivated. So first way is deactivation by releasing energy in the form of heat. Second one is deactivation by releasing energy in the form of light. So lights are generally two types. That common light is nothing but a luminescence. So if it is comes from singlet state, fluorescence, comes from triplet state, phosphorescence. Clear? Now next go through one more, coupling reaction. Excited molecule also undergo coupling with ground state molecule. Coupling reaction. So now chemical reactions. Right now what we learn? After excitation how it is coming back to ground state without participating chemical reaction. Right now see, this is photochemically excited molecule. This is photochemically excited and becomes a M star. If I write M star which is activated. So this M star is going to couple with a ground state molecule. This is excited and this is ground state. Finally both are get down into ground state. Now this is called coupling. First we are taking one reference molecule. That reference molecule is M. That molecule is get irradiated, it is get activated. After activating, now Z0 which is in a ground state. Now this excited molecule couple with a ground state molecule and both becomes ground state. Now this is your product. This is called coupling reaction. Okay. So generally see, this is a carbonyl compound. Carbonyl compound, here I am using a olefin. Now this is on irradiating. So whenever if I irradiate, what happens? See, carbonyl group is undergo excitation. This is excited carbonyl. And what about here? Ground state olefin. Only one partner is sufficient to undergo excitation. After excitation, what happens? See, this excited molecule, M star is this one. This is Z0. Now these two undergo coupling. So after coupling, what happens? See, it may give this kind of product. This is pH and this is pH. Pattern-Bucci reaction. This is called PB reaction. Only one is excited, other is ground state. This is called one coupling reaction, also called dimerization reaction. Cyclization, dimerization, all are belongs to coupling only. So this is your third possibility. Now fourth possibility, fragmentation. What it means? Fragmentation means breaking into small pieces. Means molecules get activated, then they undergo fragmentation. Means it will break some atoms from their molecule. See, this is the molecule which is undergo activation by taking photons. Now after this, it is going to break into small pieces. See, this is an excited molecule. Now it will break down into small pieces like that. Okay, so you may get A, B, C like that. What is A, B, C? Which are the fragments which are comes from excited molecule. Okay, person is taken energy and he was excited. You was taking energy from sunlight. Molecule is taking energy from sunlight and it is get activated. After activated, it is splitted down into small pieces. Split into small pieces. Why? What happens here? What is the meaning here actually? So molecule is taking excess energy, so that excess energy it is not utilizing. Then what happens? They need to burn their energy. That's why complete molecule is undergo splitting. So simply remember, person actually was rest. He was taking excess food. Then what happens? Active or inactive? Active, unstable, right or not? Stomach is completely filled. Then what happens? Stable or unstable? Unstable. Then fragmentations will take place. It will split down. Right or not? If you are unstable, then automatically fragmentation takes place. Here also same. See, person is in ground floor. He was taking excess energy. He want to control their energy. So he was taking energy. Then what happens? He was activated, entered into 5th floor, and he was jumped from 5th floor. Then fragmentation takes place. Right or not? Energy released. What is the final target? Actually was in ground state only. Unnecessarily we are giving energy. And one more time was released and came down into ground state only. Right or not? So that's why which is better state? Ground state. So you are flying, finally you will get down. Photochemistry says only one thing. You are unnecessarily jumping from one place to other step, but finally your target is ground state only. Your excitation is finally required one stability. Right or not? We are unnecessarily giving some energy to molecule. Then molecule becomes, suppose see, small kids are there in your house, you are simply playing, and if you show a new toy, what happens? You was become more anxiety. Anxiety will be created. Then person becomes unstable. Okay? Until and unless if you give one slap, it cannot be get down. Means you need to control them. So you activate them, control them. That is a process. That is photochemistry. Okay? Molecule is inactive. We are making them into active. Finally we are controlling them to get active to inactive. Actually it is inactive only. Then we are unnecessarily giving energy. Right or not? We are unnecessarily giving energy, molecule becomes unstable. If molecule unstable, it will give, they need stability. Actually it was stable only, but we are giving energy and making them into unstable. Then it is suffering from stability. That's why these chemical reactions are taking place. Take this. That is fragmentation. So best example is McLa-40 fragmentation. You know McLa-40. See, this is most important reaction. This is C double bond O pH, alpha, beta, gamma. Now this molecule is activated already, photochemically activated. Now break this bond and this one. Gamma hydrogen transfer followed by beta homolysis. That is called McLa-40. Now this radical forms a double bond. This will take one hydrogen and followed by double bond. See, this is called McLa-40 fragmentation. So photochemically this molecule is activated. This symbol wherever I write, which means it will take energy from light and it will be get activated. That is the meaning. Now it is activated. Now we are breaking bonded gamma. Gamma hydrogen transfer followed by beta homolysis is called McLa-40 rearrangement. This is PB reaction. What is PB? Paterno-Bucci reaction. Now this is McLa-40. McLa-40 reaction, Norris 2, and one more time it will comes in mass spectrometry. Many applications are there in mass. Okay, gamma hydrogen transfer followed by beta homolysis on unsaturated double bond is called McLa-40 rearrangement. Here how many molecules are there? One molecule. Now how many you are getting? Two. Means it is fragments. It is giving a small pieces. That is called fragmentation. So what is happened finally? Whatever energy is gained by molecule, that energy it was loosed. Final target is gained energy should be loosed. That is your fragmentation reaction. Then isomerization. Fifth one, you can make a isomerization. Okay, suppose see if I take a trans molecule, this is a trans stilbene. This is photochemically activated. If it is photochemically activated, what happens? This is excited state, right? Now this is get converted into, cis isomer. Okay, so molecule trans is activated. Now activated molecule get converted to other isomer. That is called photoisomerization, which means trans molecule converted to cis molecule is converted to trans. It is also one kind of relaxing energy. Clear? Now last one, this is ejection of electron. Ejection of electron is also one of the process to attain stability. Excited molecule will lose electron, it is also one kind of relaxation. See, this molecule is ground state G0. Now photochemically activated. If it is activated, what happens? Now you will get one electron or not? It is get activated. Right? It is active molecule. Active molecule, in order to attain stability, one of the electron will lose. If they lose one electron, energy will be decreases. It will come back to ground state. So we can say it is ejection of electron also one kind of stability factor. So when one of the electron is removed, what happens? It becomes a radical cation. This is the process. Here already how many lone pairs are present? 2 lone pairs which carry 4 electrons. One electron is get removed here and forms a radical cation. Ejection of electron also one kind of stability. So these are the 6 possible methods of stabilizing a molecule. Excited molecule gets stabilized in 6 ways. First is deactivation by releasing energy. Deactivation by releasing energy in the form of light. Then coupling reaction, fragmentation reaction, isomerization reaction. One more is ejection of electron. Okay, so that is about activation and deactivation. Before starting Jablonski, you have to know this. Next. So next concept, that is molecular energies. These all are basics both for photochemistry as well as UV spectra. Okay, molecular energies. What kind of molecular energies are there for a given molecule? Molecular energies. See, molecular energies are classified into 4 types. This is well known, so it will show like this. What is first one? Translational energy. ET nothing but translation energy. Then followed by rotational energy, translation energy. One more is rotational energy. Next, vibrational energy. Vibrational energy. Next, electronic energy. Electronic level energy, otherwise simply you can say electronic energy. So this is EE. These are the 4 types of electronic energy levels or molecular energy levels are present. Translational, rotational, vibrational and electronic energy levels. Molecular energies are classified into 4 types. Translational, rotational, vibrational and electronic. Okay. First you keep reading what is translational energy. Translational energy. ET. Rotational, vibrational, electronic energy level. What is translational? Translation nothing but the energy gained by a molecule for its free movement in space. Suppose see, this is a molecule which is actually in rest. So if this molecule takes energy and it start moving like this. So for this key movement, some energy is required. That energy is nothing but a translational energy. So the energy gained by a molecule for its free movement in space is called translation energy. This energy is not easy to identify. They are called non-quantized energies. Okay, so these three energies are easy to identify, easy to measure. Okay, they are called quantized energies, but this is a non-quantized. So means it will take energy, how much energy is taken, that is not possible to calculate. That is called non-quantized energies. Okay, right. Write down translational energy. The energy gained by a particle, the energy gained by a particle or molecule, the energy gained by a particle or molecule for its free movement in space, for its free movement in space, for its free movement in space, either right side or left side, like this. Okay, this is a particle which can move either right side or left side. This is called free movement. The energy gained by a particle or molecule for its free movement in space, free movement in space, is known as translational energy. So you can move either right side or left side. Now it is non-quantized. It is non-quantized. Okay, so this energy is non-quantized, means unmeasurable. Very small amount of energy, very fraction amount of energy, not possible to measure, we can ignore it. Okay, that is translational energy. Next, second one. What is one more? Rotational energy. So this is called ER, rotational energy. So what is rotational energy? Rotational energy nothing but, see, particle is take some energy and it will be get activated and it is start moving its bodily rotation. See, this is normally settle down like this. Suppose it will take energy and keep moving on space. This is called translational. So after excitation, after taking energy, if that molecule is keep moving bodily, okay, that bodily rotation is nothing but rotational energy. So in this case what happens? So the energy gained by a molecule for its free movement. Okay, now it is the energy gained by a molecule for its bodily movement in its own axis, that is called rotational energy level. Okay, this rotation energy will responsible to give rotational spectroscopy. Right? Right down. The energy gained by a particle or molecule for its bodily rotation is known as rotational energy level. So this is the body and this is the rotation. You write like this. It is rotating either clockwise or anti-clockwise with respect to this axis. It is an axis. So now we are holding that molecule is keep rotating on the axis. So if it is rotating means it is taking some energy. So with respect to that energy only that rotation is taking place, that is called rotational energy. Okay, a rotation is taking place. Atom is rotating like this. See, it is moving with respect to their axis or not. So this is called rotational. But this is called translational. Atoms are not moving but total molecule is moving bodily. This is called bodily movement and this is called rotational. Okay, take this. Now then you write it is a quantized energy. It is a quantized energy. This energy is quantized. EV, vibrational energy. It will also helps in spectroscopies. Okay, there I will explain directly that concept. Here only I am explaining basics which are related to spectra. Now next is vibrational energy. So what is vibration energy? Vibration energy nothing but the energy gained by a molecule for its periodic displacement from nucleus. Okay, suppose see, if you assume that these two are balls, now these two balls are get separated by a spring. Now if you press them and if you leave it, what happens? They will undergo complete displacement. That is called displacement, periodic displacement from nucleus. Suppose see, just assume that A and B are two atoms which are get separated by a spring like this. It is a small gap is present. Just assume that it is a gap present between these two. So now it is under rest. Then what happens? I applied some force from here. Then what happens? The gap is get decreases. When gap is decreases, you may get this one. Then if I release it, what happens? Then gap will be increased like this. Right or no? Then what happens? Is it stops? No. For this is normal stage. Now it is compressed and this is expansion. So once if you compress and leave it, what happens? It will rotate like this. So this is called vibrational energy levels. So vibration energy levels are nothing but the energy gained by a molecule or a particle for its vibrations. Okay, or periodic displacement from nucleus. See, this is a nucleus. Suppose it is a nucleus of this molecule. So when you compress them, two atoms are coming very close to nucleus, and if you leave him, then two atoms are going far away from nucleus. Now they are completely closer to nucleus, away from nucleus. That's what is called periodic displacement from nucleus. That is called vibrational energy level, and it is also quantized energy. Clear? Right. The energy gained by a the energy gained by a molecule or particle for its periodic movement from nucleus is known as vibrational energy level or vibrational energies, EV. Okay, then you take this. So this is a normal state. It is a normal state. Now this is compression. This is compression, and what is this? Expansion. So these two will happen constantly. Once if you compress and leave it, even if you expand and leave it, it will happen constantly. So from year to year, it is taking place regularly. Now bond length is decreasing or not? Now bond length is increasing. This is the nucleus of that molecule. So then finally write, it is a quantized energy. It is quantized energy. Vibrational level energy is also a quantized, means you can measurable. You can measure then how much energy required for the displacement, you can measure. Means see, if you compress them and leave it, what happens? See, there is a rotations are taking place here. Compression, normal is expansion. Scissoring, rocking, symmetric stretching, unsymmetric stretching, it will come in IR. It is actual IR spectra. Okay, so symmetric stretching, unsymmetric stretching. Okay, scissoring, rocking, twisting, wagging, all are there. So they are belongs to IR. Right now remember what is vibration energy. Bonds are start stretching now. Bonds, carbon-carbon bond is present, that maybe get stretched. So that stretch, how much energy required for stretching, that can be measurable. That is called vibrational energy. That is the meaning of quantized. Quantized nothing but energy which is analyzed or identified for the vibrations within the molecule. That is called vibrational energy. Next, last one, electronic energy. Electronic energy. So what is electronic energy? So the energy gained by a molecule or an atom for its excitation into higher energy levels. So right now molecule is under ground state, it will take energy and it will undergo excitation. That is called electronic energy level or electronic energy. Okay, right. The energy gained by a the energy gained by A. The energy gained by a particle or atom or molecule. The energy gained by a particle, atom or molecule for its excitation. For its excitation of electron. For its excitation of electron in higher excited states. In higher excited states. Next, it is a quantized energy. Next point, it is a quantized energy. So simple, you can take A will be takes energy and it is get excited. Suppose if I take a carbonyl compound, what it means, see, if I write this molecule and if I write its excited state like this, what happens? It will be get activated, that is the meaning, which means one state to other state. So here actually ground state, now it will be excited state. Now what happens here? Carry 2 electrons. This state carry 2 electron. In order to excite this electron from here to here, so we require some energy. That energy is called electronic energy level. If I put star, which means one electron is excited from one state of the molecule to other state of a molecule. That is called electronic excitation. Okay, so finally, how many types of molecular energies are there? Molecular energies are 4 types. What are they? Translational, rotational, and what is one more? This is vibrational, and what is this? Electronic energy level. And what is this? This you can neglect. Non-quantized means it is responsible for bodily movement, but that energy cannot be identified. So we can say this is only one which is non-quantized. So we can ignore this energy, but remaining 3 are quantized. So we need to focus only these 3. We can ignore translational. Why? Because the energy which is gained by this particle, it is infinitesimally very small. It is in delta. Okay, not in dou. Okay, so even in small value delta, that small value is unable to measure clearly. So that energy required for bodily movement, that energy cannot be identified. That's why we can ignore this one. We can calculate only 3. So finally we can say, what is the total energy? Total energy of a molecule. This you remember, I will ask in IR. Total energy in molecule is completely equal to sum of vibrational, first you start with rotational, vibrational, and what is one more? Electronic. It is a total energy. How much energy gained by a particle for excitation? Suppose see, when any molecule which undergo excitation from here to here, which means it is a mixture of 3. Excitation of electron is a mixture of 3. What are they? Rotational, vibrational, electronic energy level. So between 2 electronic energy levels, there is a vibrational and rotational energy levels are present. Right? That is your final structure of molecular energy. So finally we can say like this. See, this is a S0 state, and here it is S1 state, and this is S1 state. Now what are these energy levels? Electronic energy levels. Electronic energy levels are associated by, see, this is V0, and what is one more? R0. Now then followed by V1, then V2, V3, V4. Like this, many energy levels are going to come. Okay? Every vibration energy level, there is a set of rotation energy levels are present. Now what is this? V1, R0, now here V2, R0, V3, R0, V4, R0, etc. Now what is this? V5. So what is this? In between. This is V1, and here V0 is also there. Here what is this? What is this energy level? See, from S0 is nothing but a electronic state, and this is also electronic state. So between electronic state there is a number of vibration energy levels are present. These are number of vibration energy levels. Here every time you need keep on decreasing gap whenever if you are keep on moving above. Now this is belongs to V1, V2, V3, V4. Every vibration energy level. Okay, if you assume that this is S1, Now these are variable energy levels, vibration energy levels. Now this I am taking V1. Now here see this is V0 is there. Now what about these energy levels? Vibration energy levels. Vibration energy levels responsible to give rotational. Okay. So this is R1, R2, R3. Next here also same. What is this? R1, R2, R3. And every vibration energy level there is a branch of R1, R2, R3 like this. Now here see this is vibration energy level. Okay. Here what they are present? Rotational. So can I say R1, R2? Here R1, R2, R3. And here also R1, R2, R3. And even between vibration energy level you write down R1, R2, R3. Between electronic energy levels you write down V1, V2, V3. So in order to take electronic excitation there is a change in their vibrational and rotation energy level. Suppose electron is exciting from S0 singlet. It is electronic energy level. And this is vibration energy level. And what are they? Rotational. So in electronic energy level there is a branch of vibration energy levels. In vibration energy level there is a branch of rotational. Clear? In order to take electronic excitation there is a vibrational, change in vibrational and change in rotation energy level takes place. Clear? These all are vibration energy levels, V5, V6, V7 like that, Vx. This is Vx I am saying. Many, between two electronic energy levels, many vibration energy levels are present. Between two vibration energy levels, many rotation energy levels are present. This is a common thing within the molecule. This you make them thick, which means it is electronic energy level. And here also electronic energy level, this is same. You write down thick lines with a electronic energy level, normal lines with a vibrational, and write down slight lines, normal very low lying lines with a vibration. So otherwise this you extend. Here you write some little bit inner, they write completely inside. So that you can identify what are rotational, vibrational, electronic energy levels. V's R0, R1, R0, R1, R2. Where it is present? These energy levels? In between vibration or not? It is vibration. So, lowest energy is 0 calorie per mole. 0 calorie per mole. And see this is 1 calorie per mole. And see this is 2 calorie per mole. So in order to make any rotation from here to here, how much energy difference? 1 calorie per mole is required. And from here to here, same gap is remains same, 1 calorie per mole. So rotation energy level is get separated by 1 calorie per mole. Okay, two rotations, see between this, here R1, R2, R2 to R3, R2 to R4, between two vibration energy levels, that gap is maintained by 0 calorie, initially 0, from R0 to R1, 1 calorie, R1 to R2, 1 calorie, etc. Now, if you go through vibration, so V0, V1, V2. Now, this is energy order. Now, see, lowest energy carry 0.5 kilocalorie per mole. V0 having some energy in this one, 0.5 kilocalorie per mole, vibration. Okay, so from here to here, what happens? See, there is energy of 1.5 kilocalorie per mole of energy is required for make a vibration. So from here to here also approximately same, 1.5 kilocalorie per mole of energy. Okay, so approximately 1.5 means here we can make 2 kilocalorie per mole, and here this is 3.5 kilocalorie per mole. This is for rotational and this is for vibrational. And if you go for electronic energy level, so electronic energy level also represented by S0, S1, S2. Otherwise you can write E0, E1, and what is one more? E2. Like that you can write electronic energy level. Electronic energy level is high energy level where you can transfer energy from here to here. From here to here energy is remain same. So here you can say nearly 2 kilocalorie per mole. 2 kilocalorie per mole. Okay, so almost all here they carry 1 kilocalorie per mole in their ground state. Ground state electronic energy level carry 1 kilocalorie per mole. So which means from here to here 1 plus 2 total 3. So we can say 3 kilocalorie per mole is required to excite. Then from here to here 3 plus 2 5. 5 kilocalorie per mole of energy is required to excite. So this electronic energy levels in between many vibrations are there. Between one vibration energy level many rotations are there. So what is rotational energy? Rotational energy. What is rotational? Energy gained by an atom or molecule for its bodily movement or bodily rotation. Okay, bodily rotation. Take a ball, that ball is rotating in its own axis. That is called bodily rotation. Then what is vibration? Periodic displacement from nucleus. Means compression, expansion, like that. So first it will take energy, it will rotate. Then compress like that. Then finally undergo excitation. So between electronic energy levels, what they present? Vibration. Between vibration energy levels, rotational. So in order to undergo electronic energy level, UV is required. So now between vibration energy level, IR. Okay, vibration energy level is UV, only electronic spectra. And this vibration energy level belongs to IR spectroscopy. What? So that is about molecular energies. So we introduce what is photochemical reactions, difference between photochemical and thermal. Initially we given sample, then we learn what are the importance of photochemical reactions. then sources of photochemical reaction finally. So how to deactivate, activation and deactivation. So target is making activation, then after activation how it becomes deactivated by releasing heat energy, light energy, coupling, fragmentation, isomerization, one more is ejection of electron from their excited state. Later on we learn what are the molecular energies which are required for a molecule to absorb any UV visible range of energy. So it may be translational, rotational, vibrational, electronic energy level. So translation energy level is non-quantized, so you can ignore them, and remaining three different energies are becomes quantized. So we can identify and we can calculate the energy. See, we are calculating the energies, that's why it is called quantized. I not written rotational. Why? Because it is not possible to calculate. It is infinitesimally very small, not easy to calculate. So we can ignore translational. So total energy of a molecule depends on three factors. So what are the three? Only rotational, vibrational and electronic energy level, that will give total energy which is required for excitation. Excitation required three energies: rotational, translational and vibrational. Okay. So that is about this. In your next class you will see what is thermal reactions, or thermally how these electronic energy levels are get influenced. Suppose if I give thermal energy for this molecule, how either rotation energy influence or electronic energy level influence or photochemical energy level is get influenced, that we will see. Then followed by what is a Morse curve and what is difference between photochemical and thermal reactions. Then we will see what are electronic transitions. Then we will see what is Frank-Condon principle. Then followed by Hund's rule of maximum multiplicity. Then what is allowed and forbidden electronic transition. Then at last we will see Jablonski diagram. In Jablonski diagram we will see radiative and non-radiative systems. So in that we will see VC, IC, then ISC and fluorescence and phosphorescence. Later on we will see what is photochemistry of carbonyl compound. Okay. So take a break, then sir will continue.